The topic is optimal binary search tree. Already I have one video on this, but in that video I have just considered successful search probabilities, and in this video I'll be considering successful search as well as unsuccessful search probability. So I'll cover it as a very fresh topic. So the contents of this video are these. First of all, I'll explain what does it mean by binary search tree, then how do we search, how it is useful for searching, then what does it mean by cost of searching. Then next I will explain the probabilities for search, what does it mean, and also I'll explain what is optimal binary search tree and how to know its cost. Then I'll show you the dynamic programming approach for constructing a optimal binary search tree for given set of keys or given set of elements. Then that approach, I'll show you how to derive the formula for dynamic programming. Then I'll take a problem and solve. Then finally we'll see how an optimal binary search tree can be constructed by using dynamic programming approach. So in this video, I'll be deriving everything. So here you have to observe and learn how to devise a solution by using dynamic programming approach. See, most of the students want to learn dynamic programming. So for learning, practice is important. So by picking a few problems, if you study them in detail and understand how the solution is given, then you can give a solution to any new problem. Right? It's not that somebody is explaining all the problems, then you know the solutions. It's not like that. See, if you know the approach for few problems, then you take up a new problem and try to solve it by yourself. So here I'll give you a complete approach, everything I'll show you in detail, so you'll get the clear-cut idea how the approach is taken, and you can see observe the minor details also in this problem. Alright, so this will help you a lot if you are really interested in learning dynamic programming and solving challenging problems. Let us start with the topic. Here I have an example binary search tree. This is a binary tree. And these are keys, the nodes are containing keys, right? And the keys are arranged such that for any node, if you take, all the smaller keys are on the left hand side, all the larger keys are on its right hand side. So if you look at this 40, all these keys on the left side of 40, that is 10, 20, 30 are smaller than 40. And after that on the right hand side, these keys are greater than 40. And similarly, if you take 60, this 50 is smaller on the left hand side, 70 is greater, that is on the right hand side. Why? Why we have arranged the keys like this? See, it gives an advantage for searching. How? Let us see. I want to search for 30. How to search? Start from root. This is the root of a node. Is it 30? No. Then where I should look for 30? On the left hand side, because 30 is smaller than this 40. So definitely it will be on the left hand side. Go on the left hand side. Is it 30? No, 30 is greater than this one. So greater than 20, so definitely it should be on the right hand side because we have arranged the keys like that. So go to right side. Yes, 30 is found. So in this way, we can search for any element. Now for searching for 30, how many comparisons we have done? 1, 2, 3. So the element is found in 3 comparisons. If you check total, I have 7 elements. And in that 7 elements, searching for any element, that is 30, has taken 3 comparisons. Let us observe what about others. See, if I am searching for 10, it will take 3 comparisons. And for 20, it will take 2 comparisons. And for 40, it will take only 1 comparison. 30, 3 comparisons. 60, 2 comparisons. 50, 3 comparisons. So what is the maximum comparison? The maximum comparisons are 3. That is the height of a binary search tree. And that also I can call it as levels of binary search tree. This is the first level, second level, and this is the third level. So the number of comparisons required for searching any element in a binary search tree depends on number of levels in a binary search tree. Now let us learn one more thing. See, we were searching for the keys that are present here. So and they were found. So this is called as successful search. Now let us assume I am searching for a key that is 9. Let us search. Is it 9? No. Is it 9? I should go on the left hand side. Is it 9? 9 is smaller than this. Go on left side. Is it 9? No, 9 is less than this. Go on this side. There is nothing. This is null. This is end. So 9 is not found because I have reached till the end of a binary search tree and the key element is not found. So if a key element is not found, then search is unsuccessful. Alright. Then in this also, how many comparisons I have done? Maximum I have done 3 comparisons. I have checked here and here and here. So when you are searching in a binary search tree, there are 2 possibilities, like the element is found or element is not found. Let us try one more element. I want to search for key element 47. Let us start. Is it 47? No. 47 is greater. Go to right side. Is it 47? No. 47 is smaller than this. Go to left side. Is it 47? No. 47 is smaller than this. Go to left side. There is nothing. End. So search is unsuccessful. So search may be successful also, search may be unsuccessful also, right? So in both the cases, we need to know the amount of comparisons that we are doing, and that amount of comparison is nothing but the cost of searching in a binary search tree. Now one more thing. In this tree, if you observe, there are circular nodes and these are square nodes. I have drawn them in smaller size, right? So those are square nodes. What they are doing here? Do they have keys? No, they don't have keys. Then what they are representing? They are representing all those keys that are for unsuccessful search. Let us see what does it mean. See, if I am searching for a key that is 11. So 11 is smaller than this and greater than this. It will come this side. So for 11, it has terminated here. Then 12. So 12 is smaller than this, but greater than this here. So it will come on the right hand side. So it will come here. So if I search for the keys from 11 to 19, it will be coming on this side only. So I'll just make it as 11 to 19. This is representing, this node is representing all the unsuccessful search keys from 11 to 19. Then what about this? This is representing all the keys from minus infinity to 9. So if you search for any number less than 10, search will terminate here. So though we will not compare here, we will stop our comparisons here, but we will reach here, go to left side, null, and we'll stop. So that you can call it as null. Square nodes are nulls also. That null is representing all those keys for which search will be unsuccessful. Then similarly, all these are representing not one value, the set of keys for which search may be unsuccessful. If you see this last one, this is representing 71 to positive infinity. 71 to positive infinity. Any numbers you search greater than 70 in this binary search tree, the search will terminate here. So we have seen unsuccessful search are also represented as dummy nodes, just to show that this is having set of unsuccessful search keys. So now we learn one thing, that in a binary search tree, search may be successful or unsuccessful. In both the cases, we have to perform some comparisons and reach the result that key is found or key is not found. So that's all. These are the basic things that I was supposed to give you. So I have given it. Now next thing. Here I have 3 keys. 3 keys. For 3 keys, I have constructed binary search tree. So if you check, all these are binary search trees. Just pause the video and check. All these are binary search trees. So what I have to say here is that for same set of keys, there can be many possible binary search trees. If you want to know the count, how many are possible, here I have given the formula for n keys. Like here we have 3 keys, 2 into n, c of n, then plus divided by n plus 1. Then that 3 I have kept here. So this is 2 into 3. This is 2n means 2 into 3, c3 by 3 plus 1. So this becomes 6c3 by 4 and answer is 5. So you can calculate this. So for 3 keys, 5 different binary search trees are possible, and here are those 5 binary search trees. So if you have more keys, then more binary search trees are possible. Now if you observe here, the cost of searching, like there I have shown you the cost of searching, the maximum comparisons were 3, right? But here, if you observe, the maximum comparisons are 3, maximum are 3, maximum are 2. Oh, this is better. This binary search tree is better. So if you search for any key, you can get the key in less number of time, less amount of time, less number of comparison. And this is more, this is more. So the idea is for the same set of keys, when you can have multiple binary search trees, one of the binary search tree may be giving you best results, that is minimum number of comparisons. So that's it. We prefer that binary search tree. So we want a binary search tree which requires less number of comparison for searching any key element. So if you look at this example, I have 7 keys. I have arranged them like this. Now how many binary search trees are possible for 7 keys? You put 7 here in the formula and calculate it. So many binary search trees are possible, right? And one of the binary search tree, I will quickly draw it here. So if you take 70 as root and 6 as left child, and then it's left child 50, then it's left child 40, then it's left child 30, then 20 and 1. So this is also a binary search tree for same set of 7 keys. Now here if you see how many levels are there, 1, 2, 3, 4, 5, 6, 7 levels are there. So maximum how many comparisons required for searching any key? 7 comparisons are required. So the cost is high. So it means that if the height of a binary search tree is less, then the number of comparisons will be less. So height plays an important role for searching, right? So one thing we learn, the height of a binary search tree should be minimum. Now next I will show you what does it mean by probability, that is successful search or unsuccessful search probability. I'll discuss about this. For explaining successful search and unsuccessful search probabilities, I have an example. Let us look at this. See, I have 4 keys, right? And using those 4 keys, I have drawn different binary search trees also. For 4 keys, 14 different binary search trees are possible, but I did not draw all. You can try them all if you want. I have taken just 3 binary search trees. Now, first important thing, there are 4 keys, and these black nodes or square nodes are representing unsuccessful search. How many are there? 1, 2, 3, 4, 5. So if there are 4 keys, there are 5 square nodes. So if there are n keys, there will be n plus 1 square nodes. Yes. So there are 4 keys and 4 plus 1, that is 5 square nodes. Now let us talk about probability. So for talking about probability, I'll take an example. See, if you are assume that you are running a store, a shop, and you have a lot of items to sell, right? A small shop. Then how you have arranged the items in your shop? Few are on the counter, right, at the entrance point only, and few are inside the shelf, and few are deeper inside your shop, and some of the items you have kept them in stock room, right? So which items are easily reachable? The one that are there in the front counter at the that is sales counter or billing counter, that are easily reachable, right? And the one in the stock room will take time for fetching those items. So how do you keep these items? So you keep these items because depends on the frequency of their sale. So that frequency is nothing but probability of their sale. So those items who are having high probability of selling, you will keep them on the billing counter. The items which are having least probability, they are there inside the stock room, right? So that's how we arrange the items. So same way, these keys are nothing but the items, and we are searching for them, right? Fetching them or looking for them is nothing but searching. Like suppose you have a lot of items on your say billing counter, somebody asks for something, then you search, here is the item. So that's what you are searching. So you want to arrange them such that they can fetch in less amount of time. So the cost of searching should be less. And one more thing you are considering here is that a customer is asking for something which you will search and find that no, it's not available, it's out of stock. So that also you want to consider. You want to consider what is the frequency that people are asking for few things which are not present in the shop. So successful search probability as well as unsuccessful search probability, right? So what is the possibility? Based on that, you will arrange the thing. See, if some customer is asking and you are going into the stock room and checking and coming back and saying it's not there, so it will take more time, right? So if the unsuccessful search probability is high, then such things you assume they are there in the counter, near the counter. It's not there, right? Quickly you can say, check in the stock room. No, I know it's not there because we keep it here only if it's there. So that's what. So the frequency of successful search and unsuccessful search, both are important. So I have the keys here. So if you see, I have given the probabilities, both successful search probability and unsuccessful search probability. If you sum up all of them, I have taken in decimals, right? Point, because the final probability should be 1. If you add all these, that will be 1. Okay. So the final probability is 1. So that is distributed among successful search and unsuccessful search for various keys. This is the successful search probability for key 10. So let us call this as P1, probability 1, and this is probability 2, probability 3, probability 4, that is for the fourth key. Then unsuccessful search, we have one extra. Let us call this as Q1 for unsuccessful search, Q2, Q3, Q4. 1 is extra, so this we call it as Q0. So we have started from 0 to 4, right? Now, there are 5. You can say that why do you start from 1? You start from, why don't you start from 1? If I start from 1, then I have to give this as 5. So that will be greater than the key 4, right? We have fourth key only. So that's why I have started from 0. So 0 to 4, and that is from 1 to 4. So if you look at it once again, see, this is the probability of searching 10. Then what is this? The probability of searching anything that is less than 10. So that is minus infinity to 9. And this is the successful search probability of searching 40. So that is the chances that a customer is coming for a key 40. Assume like this. Then what are the chances that he is coming for anything above 40? So that is from 41 to infinity. This one, 0.05 is the probability. So this is not representing just one element. It is representing set of elements or set of keys. That is representing just a particular key. That's it. This is about the successful search and unsuccessful search probability. Now, we need to know the cost of searching. So for cost, I have trees here. See, this is the example tree. And if you take the levels, this is level 1, level 2, and this is 4 is at level 3. So I have taken levels also. And for each node, that is for key, I have taken its probability. I have mentioned it. That is 0.1, 0.2, 0.1, and 0.2. Then I have, for square nodes also, I have the probabilities. Now I want to know the cost of searching based on successful search and unsuccessful search probabilities. So let us find out the cost. So what is the cost of searching this one? It is at level 1. So just one comparison. 1 into 0.2 plus what is the cost of searching 10? That is 0.1. So, and it's at level 2. So it is 2 into 0.1. Right? Then for 30 I will take number of comparisons required are 2 because it's at level 2. So 2 into 0.1 plus 4. This requires 3 comparisons. So 3 into 0.2. So for successful search keys, I have taken this plus I should continue, but I will not do there. I will do it here plus, right? Now for unsuccessful search, 0.1. But how many comparison? See, level 1, level 2. This is not level 3, right? Don't take it as level 3 because we don't compare. We stop here only. We stop our comparison here only and try to go on left side and say key is not there. That's how it's unsuccessful search. Only 2 comparison. So what is the level if you take? I should take its level as 3, right? So this is along with the 40 and these are at level 4. So we don't take its level but level minus 1, 1 less, level minus 1. So this is 2 into and its probability is 0.1 plus then this is 2 into 0.05 plus 2 into 0.15 plus this is 4. This is 4. See, actually I should draw them like this. I should draw them till here, till 40. Okay, I should draw them here till 40. So this is 0.1 and this is 0.5, 0.05. Okay, this is at level 3. They are at level 3. Then what about these nodes? These are at level 4. So this is 4 into 0.05 and plus this is also 4 into 0.05. Okay, see these square nodes, they are also at some level, but we don't consider their level, we'll consider one less than their level. So this is the total. So what will be the total if I multiply and then add? This will be equal to, oh, I have written this as 4. This is actually 3, right? So this is 3 into. So these are at fourth level, but the number of comparisons stops here. We have to stop here, that is level 3. So it should be 3. And if I multiply this and add, the result will be 2.1. So this is the cost of searching in this binary search tree by considering successful search probabilities as well as unsuccessful search probabilities. Right, where for every key we have taken its level as the number of comparison. For unsuccessful search we have taken its level -1. Okay, level -1, whatever is level -1. So this should be extended till here. I have drawn them in small size. Okay, so level -1 we take. So this is how we got the cost. Now I will not calculate this, so you can do it by yourself. Just remember that this is at level 1, this is at level 2, and these I have to be at level 3. Okay, these are at level 3, this is level 3, and these are at level 4. So we don't take it 4 for this, we take 3 only. For this we don't take it 3, we take 2 only, because these are not reachable. We are not reaching them, we are not comparing there. So for this also you find out the cost. Now let us write down the formula for this cost. So how I have found out the cost is for keys 1 to 4. But here 0 is included, so let us write 0 also, 0 to 4. So what for 0 is, because the unsuccessful search probabilities are starting from 0 onwards, we write 0. Otherwise, the keys are starting from 1 only, but we write 0 also. So this cost is, we have multiplied every probability of a key with its level. Probability of any key is multiplied with level of that key value, right? So for key, I will say AI, that is identifier, or A elements are ABC. I am calling them as keys, but let us write it as A of I. Then plus, what about the unsuccessful search probabilities? So that also, the QI value is multiplied with level of, these are called as, square nodes are called as external nodes. So let us call it as EI, but we don't take its actual level, like this level was a 3, but we have taken 2 for this one. So this is -1. So this level should be 1 less, and this I have to do summation of all this. So let us say this is sigma, where I takes the values starting from 1 to n, and here the I value will start from 0 to n, right? So here it is not 4, it is n. Let us make it as 4n. So this is from 1 to n, that is from 0 to n. This is the formula. So what I have done, I have multiplied the probability with level, so probability with level, and unsuccessful search also probability with level, so the probability with level. This also I have to sum up, this also I have to sum up. So this is the cost formula for finding the cost of a existing binary search tree. Already we have a binary search tree and we know the probabilities, we want to know the cost. So this is the formula. All right. So now next we'll move to the next step, that is we will learn what does it mean by optimal binary search tree. See, assume that we have the keys here, and for every key there is a successful search probability as well as unsuccessful search probabilities. These are given. Then we have to find a binary search tree such that the cost of searching, this one here, if you remember, we got the cost as 2.1, that should be minimized. It means this formula should be minimized. Yes, the formula of cost should be minimum. This should be minimum. The cost for this one depends on the height of a binary search tree, which key is at which level. If you observe, root is 20, here root is 30, and here root is 40, and here 30 is at level 2, and here 30 is at level 1, and 30 is at level 3. So I have kept them at different places. So if you find the cost, you will find the differences in the cost. You will not get cost as 2.1 for this one also and this one also. You may get different cost. So as I said, for 4 keys, 14 binary search trees are possible. 14 are possible. Now we want the best binary search tree. For this, the cost is minimized. For that tree, the cost is minimized. Means this cost should be minimized. So how a tree should be constructed? So now I will reframe the statement now. A problem of optimal binary search tree is, if the keys and their probabilities are given, we have to generate a binary search tree, such that the cost is minimum. The cost is minimum. This is the problem. Now, what should be the solution? See, for solution, it means for 4 keys, 14 different trees are possible. I should draw all 14 trees and find out the cost for each tree. Then I should select the one which is giving minimum cost. This should be the approach. But this is very time consuming. You remember, for n nodes, these many trees are possible, 2n cn by n plus 1. So for 4 keys, 14 trees are possible. So if I have 40 keys, then imagine, is it practical that you try all possible binary search trees and find their cost and select the minimum one? No, it's not possible. But is it possible that we find out the best tree without generating all of them? Maybe possible. So that's what dynamic programming approach will try to give you an easier, faster method for trying out all possible binary search trees and picking up the best one without trying all of them. So imagine if you try all, how much time it will take. So we will try all of them, but not directly, indirectly. So that is the benefit of dynamic programming approach. That is the strength of DP, that you will try all of them, but not directly, indirectly. So how it can be done in this problem, let us learn. So I'll remove this and I will start explaining about dynamic programming approach for optimal binary search tree. I have written the formula here. Now for using this formula for 3 keys, just 3 keys, that is from 0 to 3, I have taken it here. Then how we can use this formula for generating optimal binary search tree? So we have to substitute the values in this formula. So let us do this one. So from this, I'll explain you what should be the approach for solving this problem. Just watch it carefully. From 0 to 3, k can take the values from greater than 0 to less than or equal to 3, means k can take the values 1 and 2 and 3. So I will substitute all of them, and from that I should take the minimum. So this should be c of 0 to 0, that is k minus 1. So what is k right now? 1. So k is 1, means this is 0, plus c of 1, 2, 3. This is the first substitution, comma, this is comma. Now k I will take it as 2. So if I take a k as 2, then this is 0, and k is 2, means 2 minus 1 is 1. Then plus c of k is 2, 2. Then j is 3 here, right? J is 3. This is the second value of k I have taken, comma. Now third value of k I will take. That is, k should be 3, so it will be k minus 1, that will be 2. So this is c of 0 to 2 plus c of 3 to 3. Then this completes all possible k values. K values can be 1, 2, 3. So I have taken this. This is for 1, this is for 2, this is for 3. So here you can see the k value, right? This term is k. This value is k. So this is k, this is k. So this is k minus 1 actually. Then at last, we have to take a w of 0 to 3. So whatever the minimum that you get, in that we can add that weight of 0 to 3. Now, from this, when I can know the answer for this one, c of 0 comma 0, that is cost of 0 comma 0, it will be nothing, that will be 0 only. And similarly, c of 3 comma 3, it will be 0 only. But what about this? I should know this value. I should know this one. I should know this one. So if I know these values, I can substitute them and I can get the minimum. Then it will give us what should be root k. And this w of 0 to 3 is nothing but sum of all the probabilities, successful as well as unsuccessful, all together, right? Now, I should know this, right? So if I have to find out this one, I'll try to expand it here only. Just watch. So if I try to expand here, c of 1, 2, 3, this is nothing but minimum of k takes the values greater than 1 and less than or equal to 3. So what are the possible values of k? K can take the value greater than 1, means 2 as well as 3. So this has to be c of, first of all, k value is 2. So this will be 1 comma 1 plus c of 2 comma 3, and next value is k value, I will take it as 3. So this will be c of 1 comma 2 plus c of 3 comma 3. Then plus weight of 0, 1 comma 3, 1 comma 3. So from this you can see that just to know this value, again if I expand, I have to know more values. I should know 1 comma 1 and 3 comma 3 also. Then this is only for this one. Then I should know this value and this value and this value. This value, that is 2 to 0 to 2. So many values I should know. If I expand them, then they will expand like anything. So for finding the cost of 0 to 3, this is the formula. In this, I don't know these values. So I should find out these values. And this again can be done using formula. Again, it expands like anything. And from this again, if I take 2 comma 3, again it will expand like something. So if I want these values, I should first know these values. So that is the point. That is the point. So it means for knowing the answer for a larger value, I should know the value for answer for smaller values first. Like these are smaller. So you can see that this was from 0 to 3 and it became 1 to 3. So it is reducing. So if I know first smaller values, then I can substitute and get the answer. Then I can get the larger value. Yes, this is what the approach dynamic programming takes for solving the problems. So if you expand all these formulas and see, then what are the values that we need? I will list them here. So from this, basically you need C of 0, 0, C of 1, 1, C of 2, 2, right? And C of 3, 3. You should know these values. Some of them you can see here, 0, 0, 1, 1, 3, 3, 2, 2 will also come if you expand any one. Then after that, you also should know that is 0 to 1 with a gap of 1. That is C of 1 to 2 and C of 2 to 3. This is a gap of 1. See, the difference between these two was 0. Now difference is 1. Then C of 0 to 2 and C of 1 to 3. The gap difference is 2 here. Then finally you can know C of 0 to 3. So first find out these, from that you can know these, from that you can know these values, then finally you can know. So it means to solve this formula, you should solve this smaller formula. For this formula, you should solve this smaller formula. So if you already have smaller values, you can substitute and put them back and get the final answer. That's what we need, the values. So these values we need. So if you observe and say that this is I and this is J, difference between I and J is 0 here. So J minus I is 0 here. Here J minus I is 1 and here J minus I is 2 and here J minus I is 3. So I should find out the values with a difference of 0, difference of 1 and difference of 2 and difference of 3. Because always I will be less than J, right? Always I will be less than J. That's why I'm not getting all possible combinations. Just I am getting this much. So if you know these values, then you can get the answer. We want the answer for this one. So now we will not be using formula, we will be filling table. And that table we know very well that it is from the formula only. So when we solve the problem, we will fill the table. Now one more thing in this one. Apart from finding the cost, we should also know who is giving us minimum cost. Means which k out of these 3 k's, which k gives minimum cost. From that we will select it as root. So we should monitor that also, observe that one also. Then also in the formula we have weight values. So how to know the weight? See, if you observe, if you take weight of 0, 2 and weight of 0, 3, then what is the difference? See, these are the weights. So if you take 0, 2 and 0, 3, what is the difference? So what is this? Q0 plus P1 plus Q1 plus P2 plus Q2. What about this? Q0 plus P1 plus Q1, P2 plus Q2 plus P3 plus Q3, right? So if you observe these two, then this is same in this one and only P3, Q3 is added. So weight of 0, 3 can be taken as weight of 0, 2 plus P3, Q3, right? So it means weight of any I, j can be taken as weight of I, this is j minus 1 plus, okay, j minus 1 plus Pj, Qj. So this is how we can modify the values of W. So it means if you found one of the W value, you can know the next value by this method, right? So if you already know 0, 2, you can easily find 0, 3. So finally, I can say that we have to find out cost, weight for the formula, plus who should be a root. So now I have explained you what should be the approach. Now I will take an example problem and I will solve it. Let us take a problem and solve it using the formula we have already seen, and also I have given you the approach. Now I will solve this problem and also I will construct a binary search tree, that is optimal binary search tree. So let us look at the problem. First of all, see there are 4 keys given, 10, 20, 30, 40, right? And these are successful search probabilities, right, of first key, second, third and fourth key. And these are unsuccessful search probabilities that are QIs, that are starting from 0 onwards, like one extra unsuccessful search probability will be there. So this is 0, 1, 2, 3, 4. Actually, the probability should be in decimal point. Probability should not be greater than 1, right? These are in decimal point, but working with the decimal point will be difficult. So actually, if you add all of them, total is 16. So if you divide them by 16, every value by 16, you will get the actual probability. So they are multiplied by 16 to get the integer number so that you can easily calculate them. Now, for solving, as I told you the approach, I have taken all the values, the weight and the cost and the root, who should be a root. So all these values are filled here. And this is 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Difference between I and j is 0. 0, 1, 1, 2, 2, 3, 3, 4. Difference between I and j is 1 and 2 and 3 and 4. I have to fill up this table. Finally, I need the cost for 0 to 4. That is 4 keys are there. So 0 to 4 is here. So if I can get this answer, then I got the answer. I am not using the formula directly, but indirectly I am using the formula by filling this table. Let us fill up the values. So first of all, W value I will fill up. See, W of 0, 0 is Q0 plus nothing is there, right? 0, Q0 will be there. So it means 0, 0 is Q0. W of 1, 1 is Q1 plus nothing is there. 1 is the last one, starting from 1 and ending at 1. So this is just Q1. So it means this W of 0, 0 is, this is 2 and this is 3. 1, 1 is 1 and this is 1 and this is also 1. Okay, 2, 3, 1, 1, 1. So W values are just first Q values. So that is filled. And what about the cost? Cost of 0, 0. So cost of 0, 0, if you take, K takes the values from greater than 0. Greater than 0 means 1, but less than equal to this one. So there is no K value possible. So these costs are zeros. So initial values are all zeros. These are all zeros. All right. So these are all zeros. That is filled. First row is filled. Now next row, this one. For this, first of all, I will find out the W values. Then I will show you cost and the root values. Roots also I made them as 0 here. Now here, W of 0, 1. So if you remember, I have shown you that W of I, j is nothing but W of I, j minus 1 plus Pj and Qj. Right? So W of 0, 1 will be W of 0 and j minus 1 is 0 plus P1 plus Q1. So this I can obtain from this one. 0, 1 I can obtain from 0, 0. 0, 1 I can obtain from 0, 0. So this plus P1, Q1. These are P1, Q1. 3 plus 3, 6 and this 8. And if I take this, for this one, this is 2, 1, 2. So P2, Q2. So 3 plus 1, right? 3 plus 1, 4, 5, 6, 7. This is 7. And this value, 2, 3, 2, 2 plus P3, Q3. 1 plus 1 plus 1. Total 3. Total 3. That is 2 and this is 1. Now this one, 3, 3, 3, 4. So 1 plus 4, 4. So 1 plus 1, right? 2. And that is 1, 3. So this is 3. W values, I have filled them like this. Now even I can fill up all these values, W values. So let us finish them. Okay, I'll fill up all these values. Then I will fill up cost and the root. So weight can be already known. This is 8 is there. Then 2, 2 I have to fill up. That is 3 plus 1, 4. 8 plus 4 is 12. 7 plus 2 is 9. Then 3 plus 2 is 5. Then next, this one, 12 plus 3, 3. 3, 3 is 2. So this is 14. And this is 4 comma 4. So 9 plus 2 is 11. Then this one, 1 comma 4, then this one is 16. 14 plus 2 is 16. So W values already have filled them by using this formula. This formula, you can see this is the formula, right? Now, I have to find out cost. So I should start from here. I will find all these costs and I will fill up them also roots. So let us do it. Let us find C of 0 comma 1. So for that, first of all, I will write down the formula, right? So you should look at the formula. From that we will do it. This is minimum of k takes values greater than I less than equal to j. And this is C of I comma k minus 1 plus C of k to j, and outside the bracket is W of I j, right? This is the formula. Now, keeping this formula, I will be using it for finding all the values. Let us start C of 0 comma 1. So here write C of 0 comma 1 is minimum of k takes the values greater than 0 less than equal to 1. So what are the possible values of k? Greater than 0 means 1, 1 to 1. So only one value it can take. So this will be C of I is 0. K, I said it is 1. So 1 minus 1 is 0 plus C. K is what? 1. K is 1. And J is what? 1. Plus, so outside the bracket we have plus W of I comma j. I comma j is 0 comma 1. 0 comma 1. This is what the formula we got. So as there is only one value, so that is only the minimum value. So let us find out minimum of, do I have C of 0 comma 0? Yes, it is 0. 0. Then C of 1 comma 1. Yes, I have 0. 0. Plus weight of 0 comma 1. Weight of 0 comma 1 is 8. Here we have 8. 8. Then what is the minimum of this? 0 only. So this is 0 plus 8 is 8. So cost of 0 comma 1 is 8. First value we got. If you observe in this one, only k value, one value is possible. Only one value is possible. So here, this is becoming 0, 0. This is becoming 1, 1. Right? Now let us try for C of 1 comma 2. 1 comma 2. I will find out this one. So what I will do is, I will just modify it. Okay? 1 comma 2. This is 1, this is 2. And this is 1, this is 2. K can take the values greater than 1, less than equal to 2. So only 2 it can take. Then this is C of I. I is what? 1. K minus 1. 2 minus 1. 1. C of K. K is a 2. 2. And C of J. J is 2. So this is 1 comma 1. 2 comma 2. And a weight of 1 comma 2. Weight of 1 comma 2. So C of 1 1. 0. C of 2 2. 0. Minimum of 0 is 0 only, right? Weight of 1 2 is 7. This is not 8, this is 7. This one, right? Now add this, what is the result? 0 plus 7 is a 7. So I got the same value here. So this means that if I try for C of 2 3 also, I'll get weight only, because there is only 1k value possible, and that we are getting 0 only. So this will be same 3 3. I save the time. I have observed that it is coming same thing. So I have directly written the value. So I have saved the time. Now 1, 2, 3, 4, 5, 6 values I have to find out. Next 0 to 2. Let us find out 0 to 2. I'll remove this and I'll find out 0 to 2. Now what should be the root values here? See, the minimum value here, the minimum k value was 1. Here k we have taken as 1. K here we have taken as 2. And here 3. Here 4. Now here in this one you cannot see the difference. Next level, when I find the values for these, that time you can find out how we are getting root value. Okay. So just I have written 1, 2, 3, 4. Just leave it. Okay. Now let us find out C of 0 comma 2. So this will be little lengthy. C of 0 comma 2. Minimum of k takes the values greater than 0, less than equal to 2. So what are the values k can take? 1 and 2. 2 values it can take. So in this I should take k as 1 as well as k as 2. 2 times I have to try this one. So let us take C of 0 comma k as 1, 1 and 1 means 1 minus 1 0, plus C of k is 1, 1 comma 2. This is I, this is j, remember this, and right now k is 1, we are taking 1. So this I have finished. Now k as a 2 we will take 2. In this one you substitute 2 here. C of 0, 2 minus 1 is 1, plus C of 2 comma j is 2, 2 comma 2. Then outside this, weight of, that is 0 comma 2. So let us substitute the values and see minimum of C00. From here I got the value. See, I am finding this one, and for this I should know this value. That is helping me. Already I know the value. Then I can use it here. That's what. C of 0 is 0. C of 1 comma 2 is 7. Plus C of 0 comma 1. C of 0 comma 1 is 8. Plus C of 2 comma 2. 2 comma 2 is 0. Okay. Then plus weight of 0 comma 2. Weight of 0 comma 2 is how much? 12. This is 12. So this is minimum of, right? Which is minimum? 7 is minimum. What was the value of k here? If you remember, k I have taken as 1 here, k I have taken as 2 here. Yes, k as 1 has given me the minimum value. So this is 7 and plus 12. So this is 19 and the k value is 1. So I am filling up, watch here. This is 19. And who should be root? Minimum 1 should be root. So who was minimum? K was 1. K is 1. That's it. So that's how whoever is giving minimum value, that we will take here. And most of the dynamic programming problem, we do it like this only. Whichever value is giving minimum, that we will take it there. Now I will not find out these. You can follow this formula and you can do it. I'll fill up these values. Then I will find out these 3 values finally. Okay, these 3 values. So let me remove this and find out C of 0, 3. If you want to see the value, this value is 12, 2 and this is 8, 3. So if you follow this method and get the answer, you will get those answers. I'll remove this and find 0, 3. C of 0, 3, that is minimum of k takes the values greater than 0, less than equal to 3. So what are the k values possible? First time k value can be 1 or 2 or 3. 3 values are possible. So if I put 1 there, then it will be C of 0, 0 plus C of 1, 3. Then next is comma, next value is C of 0, 1 plus C of 2, 3, comma, C of 0, 2 plus C of 3, 3. Here k value is 1, k value is 2, k value is 3. I have tried all of them. Then out of all these, whatever the result we get, in that I have to add W of 0, 3. Let us put the values here. So I'll directly put the value below this one. This is 0 and 1 comma 3 is how much? 12. So this is 12. This 0 comma 1 is 8 and 2 comma 3 is here, that is 3. Okay. Then 0 comma 2 is 19 and 3 comma 3 is 0. So if I put the values, I'll separately put them here. Minimum of 0 plus 12 is 12, comma 8 plus 3, that is 11, then 19. Okay, then plus W of 0 comma 3 is 14. So out of this, which is smaller? This one. For which value of k? 2. So what is the answer? 11 plus 14 is 25. So this is 25. Who gave 25? Which value of k has given 25? The value of k which has given 25 is 2. So write 2 here. For saving time, I leave it. You find out whatever the value you get, you put it. Then finally, I'll do it for this one. So directly I will write down the answer. This is 19, 2. Okay. Just like this. You have to start from 2 onwards, not from 1 onwards, because this is 1 to 4. So 2, 3, 4. K value can be 2, 3, 4. Substitute and you can get it. Now let us try this one. C of 0, 4. So what are the values k can take? K should take the values greater than 0, less than equal to 4. See, this is 0, right? If it is 1, greater than 1. Okay. So whatever the initial value is. So k can take the values 1, 2, 3 and 4. So 4 values are possible. So in this formula, I should try out all. So first will be C of 0, 0 plus C of, this is 0 now, so what is 1, 4, right? C of 0, 1, then this will be 2, 4, okay? Then this is C of 0, 2 and C of 3, 4, then comma, comma, C of 0, 3 plus C of 4, 4, right? Then plus weight of 0, 4. Here I have taken the k value as 1 and 2 and 3 and 4, right? So let us put the values and get the answer. See, C00 is 0 plus C14, C1 comma 4 is 19. So total is 19, this one is 19. Then C of 01, C of 01 is 8. C of 24, C of 24 is 8. So this will be 16. C of 02 is 19 plus C of 34, C of 3 comma 4 is 3. So this is 22. Then C of 03 is 25 plus C of 44 is 0. This will be 25. So if I take minimum of, right, this is how much? 19, 16, 22, 25 and plus weight of 04, how much it is? 16. Then which is minimum? This one. For which value of k we got this as minimum? 2. So this k value is 2. So answer is how much? 16 plus 16, 32. So answer is 32. And what is the root? Who has given us minimum value? K value as 2 has given us minimum value. This is 2. That's it. So we got the table filled by using the formula. If you observe, we have started from the smaller values, then we got the larger value. So the efforts that you are putting in here are less. If we would have started from here, it was difficult to solve. We could not have solved it easily. So when we are calculating some higher value, these lower values are useful because already we have calculated them. So this approach, we call it as tabular approach. Dynamic programming follows tabular approach. So it starts from lower values to higher values. Now we have the complete data available. The cost of a tree, we got it as 32. So as I said that the probabilities are multiplied by 16 and kept there to avoid decimal values. So this result should be divided by 16. So 32 by 16, cost is 2. So the minimum cost of an optimal binary search tree is true. So if you observe this, we are always taking minimum. So it means we are taking the one which is giving us best result. Are we trying all? So if you start from the lower values and reach the higher value, if you can see that we tried all possible routes. Yes, we are trying all possible routes. As I said in the beginning that we should try out all possible binary search trees and pick up the best one. So yes, we have tried all possible binary search tree. Root should be first key or second key or third key or fourth key. Which one it should be so that we get the minimum. So we got 16 plus 16, 32. Who gave minimum? 2. So based on the cost, we are deciding. So indirectly, we are trying out all possible binary search trees. Now, last thing, what should be the tree? So from this data, we already have the data. Now we can take the decisions and form a optimal binary search tree. So I'll remove this and I'll form optimal binary search tree for these keys 10, 20, 30 and 40. Let us generate our optimal binary search tree. For what keys? 1, 2, 3, 4. So we have to find out root for keys from 0 to 4. Why 0? Yes, this unsuccessful search probability starts from 0. For everything we have started from 0. So root is also 0 to 4. Okay. Now for 0 to 4 in the table, do you have any value? You got the value which gives minimum? Yes, 2. So root should be 2. 2 means second key, that is 20. So I will write 20 here. 20. So if you remember in the formula, when root is a second key, here it is second key, right? Root is 2. So the left hand side value will come this side, right hand side values goes on that side. So what comes on this side? So I'll write down this one. Root of 0 to k is a 2 here, right? So this should be 1. And k is a 2 here. So this should be 2 to 4. If you remember, whatever the k is, left hand side is I to k minus 1. This is k to j. Right? Same method, same, based on the formula. Now here I have 0 to 1 and this is 2 to 4. So as a 2 is a root, so only one key is left on the left hand side. Now what is a 0, 1 in the table? R of 0, 1 in the table is 1. Yes, first key. What is the first key? 1, 10. So here key value is what? 10 and the k is 1. So we have taken decision. How we have decided who should be in the root? Table gave us. So we got a decision, we have taken a decision based on the data that we have. Now 2, 4, who should be root? 2, 4 means we have how many keys now? That is 30 and 40. Two keys are there. Which one should be root? Table will tell you. Based on the tabular data, you take the decision. 2, 4. So 2, 4 is here. Root of 2, 4 is 3. This is 3. Third key. So which is the third key? 30. So who is k here? K is 3 as per this value. Then 40, where it will go? On this right hand side. So right hand side, there is only one key remaining. I will not write down these values. So I will directly fill up this right hand side, that is 40. Only one key is remaining, right? So I started from 0 to 4. So 0 to 1 this side, 2 to 4 on that side. 0 to 1 gave me one key. So this is finished. I stopped there. And 2 to 4 gave me one key. So I stopped here because only one key is remaining and 40 definitely come on the right hand side. So already I have taken it. If you want to see this further, as key is 3. So on this side, if you take, this is R of 2, 2 and this is R of 3, 4. So who is R of 3, 4? That is 4. Yes, we got 4. So no need of this. This is the null value, right? That is external node. So this is the tree. So this is a optimal binary search tree with 20 in the root, 10 on the left side, 30 on the right side, 40 on the right side. So this is the optimal binary search tree based on the successful search and unsuccessful search probabilities. This is the optimal binary search tree which takes minimum cost. Alright, so as if we tried all possible binary search trees and we have taken the best one. It is just like that. If you see the approach we have taken, we have found out all possibilities and took the minimum one. So this is the approach of dynamic programming and we have solved one of the problem using dynamic programming. Now if you have similar problem, see that if it matches with this one, then you can apply the same strategy there. That's it. So that's all in this video.